Hey everyone, in this video I'm going to quickly run through the questions from lecture 6 and how to answer them, which is our first lecture on the p-block elements. So question 1 is asking us to determine the oxidation state of various elements in ions and compounds, and it's asking us to state the oxidation state of the element highlighted in red, but to do that we're actually going to have to work out the oxidation state of all the elements. And down the bottom I've taken a screen grab complete with words, grammatical suggestions from the Word document I've put on Blackboard, the help sheet, and these are the 10 rules to working out oxidation states. So we'll run through them quickly first. And the first is that the cation is always written first in the formula, followed by the anion. How does this help us work out the oxidation state? Well, we know if we take E for example, that the sulfur is going to be the cation and the oxygen is going to be the anion. So we already know that the sulfur is going to have the plus oxidation state. So that's nice. It gives us an idea of what's going to have plus, what's going to have minus. The oxidation state is always 0 in a free element. So the atoms in helium or N2 are all 0. The oxidation state for single atom ions is equal to the charge. So we'll discuss that more when we come to D. Hydridic hydrogens have an oxidation state of -1 and protic hydrogens have an oxidation state of +1. This we talked about in the third lecture, the hydrogen lecture, and it was to do with whether hydrogen is the more or less electronegative atom. Rule 5 is that the oxidation state of oxygen is usually -2. There are a couple of exceptions to this, though, but it's you'll be able to notice them usually. 6 and 7 are quite nice and easy, and there aren't so many exceptions. Oxidation state of group 1 is 1, and of group 2 is +2. The oxidation state of group 7 is usually -1. This one does have quite a few exceptions. So with fluorine, it's the most electronegative, so it's always -1. However, things like chlorine, if they're bonded to oxygen, oxygen's more electronegative, so then it doesn't have -1. And we'll see in the next lecture as well, when we're looking at group 7 or group 17 even, is that you can get into halogen compounds where they bond to each other. So obviously they're not all going to be -1 then. The sum of oxidation states in a neutral compound is 0, and the sum of oxidation states in a charged polyatomic ion is equal to the charge. And we're going to be using those two for working through all of these. So let's start with A and work through it. So the cation is written first in the formula, so we know the hydrogen is going to be positively charged, therefore it's a protic hydrogen and have an oxidation state of +1. And since there are 4 hydrogens, that means that the contribution of all the hydrogens to the oxidation state is +4. The oxygen, that's an anion because it's written at the end. Rule 5 says that the oxidation state of oxygen is usually -2, which would be correct in this case. There's nothing funny going on. And since there are 6 of them, the contribution of the oxygen is -12. And then we look at rule 9. 9 or 10, see if it's charged or not. We can see it's neutral. So rule 9 says that the sum of oxidation states has to add up to 0. So we see that we're at -12 because of the contributions of all the oxygens, +4 because of the hydrogens, leaves us with the phosphorus having to contribute +8. And since there are 2 phosphoruses, we half it. So each phosphorus is in the +4 oxidation state. Moving on to B, it's a xenon hexoxide and a 4- anion. So in this case, rule 10, the sum of oxidation states is equal to the charge. So we're actually looking at the total oxidation state to be -4. And we can do it exactly the same as last time. So the oxygen is the anion, has an oxidation state of -2. Since there are 6 of them, add up to -12. And this time, instead of trying to get to 0, as we said, it's got this charge, we want it to add up to -4. So that means the xenon has to be +8. And this is just about the only element you'll see reaching +8. It's the highest oxidation state in the periodic table. And it can only be reached by the noble gases, and not even all of them. I think xenon is the only element that can do it. Moving on to C. We can actually be a bit cheeky with this one, make it a bit easier for ourselves. So because of 10, the sum of oxidation states in a charged polyatomic ion is equal to the charge, we don't necessarily have to work out the oxygen and hydrogen separately. Like, we know the hydroxide anion is OH minus, therefore the oxidation state for the whole OH anion is going to be -1. If you want to work out why this is yourself, we can see that oxygen always has the -2 oxidation state, and the hydrogen in this case is protic, so it's +1, and it's got the minus charge. So if you see things like this tin hydroxide complex and you see the OH anion as part of it, you can be a bit quicker and just say that the oxidation state of the hydroxide anion as a whole is -1. There are 4 of them, so the contribution due to the hydroxides is -4. And since it's a charged complex that we're looking at, and we'll talk more about our complexes in the D block when we get into coordination chemistry, the whole charged complex is 2-, so we want it to add up to -2, therefore the tin has to be +2. D is not such a nice one. So it's something I said when we were doing the questions, the S block as well, that the oxidation state is pretty much always a whole number. It shouldn't ever be a fraction, but unfortunately in this question it is. So I won't put a question like D in the exam if we're looking for oxidation states. I'll make sure it's always a whole number. But it's kind of helpful because it shows in this case what happens with an element and an anion, but I don't think it's very nice of them to put it in. But anyway, we see by rule 3 that the oxidation state for single atom ions is equal to the charge. So it adds up to the charge is 2-, so we know that it needs to add up to -2. There are 4 of the seleniums, therefore -2 divided by 4 is -0.5 or -0.5. So as I say, it's not very nice that they've not done whole numbers, and I won't do that to you in the exam. Then finally, E and F are both quite simple, but they show how one element can have 2 different oxidation states in compounds. So they're both neutral, they're both adding up to 0. So again, oxygen's -2, there's 9 of them, so it adds up to -18 for its whole contribution, means the sulfur has to be +18, and divided by 3, we see that in this case the oxidation state of sulfur is +6. Now in the S2Cl2 compound, the chlorine is the anion, follows the rule of rule 8, the oxidation state of halogens is usually -1, so each chlorine's -1, the whole contribution is -2, therefore the sulfur has to make it neutral, +2, and there are 2 of them, so that's in the +1 oxidation state. So that's just a not so quick go through of how to calculate oxidation states, and the selection here is about as broad as it can get, so if you can do these you should have no problems. Question 2 is asking about the trends in first ionisation energy. So this is almost going back to what we did in the very first lecture, the revision of general periodicity trends. But as I said in the videos of the lecture, these sorts of trends are really important in the P block because it shows why in one group, such as this one, you can go from non-metals to metalloids and metals all in one group. So part A is pretty straightforward. One of the rules of the ionisation energy trends was that the first ionisation energy decreases down a group, and this is because the valence electron is much further away from the nucleus. So then, starting at the lowest and increasing, we just start at the bottom of the group and go up. So it's bismuth first, followed by antimony, then followed by arsenic, then phosphorus, and then nitrogen. So very simple, follows the trend, increases from the bottom to the top. Now part B is a bit trickier. it's got one little thing you need to be aware of. So usually the trend is that the ionisation energy increases going across a period. So in that case, we'd start with carbon, and as we go across the period, the first ionisation energy increases. However, this is not 100% correct, because something strange happens with these two. And that comes because nitrogen has a half-filled orbital, and half-filled and completely filled orbitals are much more stable. So if we look at the p orbitals for these, nitrogen has an unpaired electron in all of these, and it maximizes the parallel spins. So this is actually a lot more stable than it generally should be, whereas oxygen has an extra electron which is paired, and this means that the first oxidation state of the first ionization energy of oxygen is actually slightly lower than you'd expect, conversely the one of nitrogen is slightly higher than you'd expect, and this means that nitrogen and oxygen switch places. So in this case, the correct answer is actually carbon, then oxygen, then nitrogen, and then fluorine. And this is then because of the extra stability offered by the half-filled orbital of nitrogen. Question 3 is looking at the p block oxides, and we have to work out which are acidic, which is amphoteric, and which is basic. Now the p block contains oxides, all three: acid, acidic, basic, and amphoteric. And I've got the p block key here from the lecture videos that's coloured in which ones are acidic, which ones are amphoteric, and which are basic. So in general, it's quite easy to tell the acidic ones, because they follow this line here that non-metal oxides are acidic. It then gets a little trickier because there isn't such a distinction between which are basic and which are amphoteric. So the general definition was that very electropositive metals make basic oxides, whereas other metal and metalloid oxides are amphoteric. And we can see actually that there aren't so many basic oxides in the p block. There's just bismuth, thallium, and indium. So it's just one of those things to remember, I guess, is this one there is a pattern, like as you go to the bottom left, things become more electropositive, and that's why the basic oxides are found around here. But then when you look at it, you'd almost expect lead to be a basic oxide as well, and we can see that this one actually has an amphoteric. So it's best just to remember that the non-metals are acidic oxides, the rest of them are probably amphoteric oxides, and then bismuth, thallium, and indium are basic. So let's apply that to A, B, and C. So the first one is an oxide of phosphorus. Phosphorus we can see here, it's the second one in group 15. We know it's a non-metal, so this is an acidic oxide. B is asking us about an oxide of bismuth. Bismuth is right at the bottom of group 15. So where it's right at the bottom, we know it's going to be more electropositive. So you could guess from this that it's going to be a very electropositive metal. So it has a basic oxide. And the other way is, as I say, if you just remember these three, then you know that bismuth oxides are basic. And then finally we've got germanium. So germanium is a metalloid, and it's kind of in the middle. So that one is an amphoteric oxide. So that's as simple as it gets. As I said, if you remember the trend, that the non-metals are acidic, and then as you go further to the bottom left of the p block, you're more likely to find these basic oxides, and everything else is amphoteric. So in question 5, we're looking at the diagonal relationship between beryllium and aluminium and giving evidence for why it exists. So we haven't talked about the diagonal relationship before, but we have seen evidence of it already in the lectures. So what a diagonal relationship is this idea that between periods 2 and 3, there are pairs of elements that are diagonal to each other, such as lithium and magnesium, and as highlighted in this question, beryllium and aluminium, where they behave quite similarly to each other. And the rationale behind this is that as we go across a period, I'll change this to red actually, that'll be much easier to see. So if we go across a period, electronegativity increases and the covalent character of bonding increases. And as we go down the group, these things decrease, the electronegativity and the covalent character of bonding decreases. Therefore, as we go down and they decrease, and then across and they increase, it means that elements diagonal to each other kind of end up with similar electronegativities and amount of covalency, and they therefore behave rather similarly to each other as well. If we go back into the lectures on the S block elements with this sort of critical eye, you will actually see that there are a lot of similarities between lithium and magnesium. So when we talked about lithium being an exception because it behaved differently to group 1, we were looking at things like how the nitrate decomposes upon heating to the oxide rather than the nitrite. And if you look at magnesium nitrate, that also decomposes upon heating to the oxide rather than nitrite. So if you're more interested in the diagonal relationship, there is about half a page on it in the textbook on page 1196, looking at the lithium-magnesium diagonal relationship and giving evidence for that. But then in this question, on this slide, we're going to do a similar thing, but with beryllium and aluminium. So what are the similarities? What's the evidence? Well, if we look at how we called beryllium exceptional, and then comparing those exceptional traits to aluminium, we do find a few things. So we said that the group 2 oxides are generally basic. They only react with acids, whereas beryllium was amphoteric, and that's what marked it as an exception. Well, as we saw in one of the previous questions already, the aluminium oxide is also amphoteric, so that's good evidence. Both of their oxides are amphoteric. Another one is the bonding. So group 2 was mainly ionic bonding, and we said beryllium was exceptional because its compounds had quite a lot of covalent character to the bonding. Now, aluminium is exactly the same. The structures it forms are rather covalent. There are exceptions, like we'll see in the next question, I believe, actually. But the aluminium bonding has a lot of covalent character. And then leading on from this covalent bonding, and finally, is the tendency to make polymers and dimers to make up for any electron deficiency that may arise. So if we look at the chlorides in each case, with beryllium chloride, we looked at it before, and it had a polymeric structure where it was beryllium centers with these bridging chlorines, like this. And then that went on for, a long way. It's a polymer. And when we looked at the bonding, we saw that one of the chlorine bonds around each beryllium center is actually what we called a dative bond. So, the lone pair coordinates with this empty p orbital on beryllium. And we saw exactly the same thing when we were looking at aluminium chloride in the group 13 video. That made dimers. It was Al2Cl6, and that was in exactly the same way. So we'd have an aluminium, running out of space to draw it. There we go. It would be 2AlCl3. Running out of room a lot. 2AlCl3 monomers would dimerize because, as it is, it would be electron deficient. So again, we form this dative bond from a chlorine to an aluminium center in exactly the same way as we get the polymeric structure of BeCl2. So there's the diagonal relationship, and there are some quite strong evidence between beryllium and aluminium having this relationship. So I said in the explanation of the last question, not all of aluminium's compounds are covalently bonded, and this is the answer to this question in short. So question 6, we're looking at aluminium fluoride and how it sublimes at over 1,000 degrees and is insoluble in benzene, whereas the chloride of aluminium melts at a much lower temperature and does dissolve in benzene to give dimers. So it asks us to explain this and give reasons for the differences in bonding. So, well, yeah, the explanation is given already in the question. They're different because of the differences in bonding. So we can say aluminium fluoride, which is AlF3, has more ionic character, or is ionic bonding, whereas aluminium chloride, Al2Cl6, has a much more covalent character. And because of this, we know ionic bonds are really strong. That's why it has such a high sublimation temperature at like 1000 degrees. Whereas the covalent bonding in aluminium chloride is much weaker, and that's why its melting point is much lower. We can also, explain this actually for the solubility of benzene as well. So ionic compounds usually dissolve in polar solvents. So these are things like water. I'm not going to ask you about polar solvents in the exam. But yeah, polar solvent is something like water where you have partial charges on the elements or the atoms of water. So in water, the oxygen has a delta minus charge and the hydrogens have a delta plus. And ionic structures like dissolving in these because the ions themselves have charges. So the charged nature of the solvent helps stabilize it. Benzene, on the other hand, is not a polar solvent. It doesn't have these small charges. So trying to dissolve something with really big charges in something that can't stabilize this, doesn't happen. It's why it's insoluble. But the covalent nature of the aluminium chloride bonds, can be dissolved in something non-polar because the covalent nature, it doesn't have these charged bits, so it doesn't need the charged solvent to stabilize it, if that makes sense. But I'm not going to be asking you about polar solvents and things like that. So, you might come across it in organic chemistry, but I won't ask that in the exam. It's just to give you more of an explanation for this question. But giving reasons for the differences in bonding is really what we're focusing on here. So you say that aluminium fluoride is ionic, it's why it's got these really strong bonds. The chloride is more covalent, that's why its bonds aren't so strong. The very easy way to explain it is with electronegativity. So I've put the triangle here so we can draw on it. Let's get the electronegativities of the elements here actually, so you can do it along at home if you would wish. So we've got aluminium, the electronegativity is 1.61. Fluorine, the electronegativity is 3.98, and chlorine, the electronegativity is 3.16. So then if we plot the differences and the average on this triangle, we see that the average between aluminium and fluorine is 2.8, so it's somewhere around here, and the difference is 2.4. So that is right up here for aluminium fluoride. Whereas if we do it with the chloride, the average is 2.65, so that's more like here, and the difference is only 1.5. So here we can see it's much lower, and it's just this big difference in electronegativity that's present in the aluminium fluoride means it has very ionic bonding, whereas the electronegativity difference between aluminium and chlorine isn't so great, so it has a much more covalent character. And that's why it forms these covalent bonds and behaves completely differently. So question 7 is asking essentially, what is the inert pair effect and why does it happen? Now, if I was to ask a question like this in the exam, the way I'd probably grade it is that a third of the marks, say if it was for 3 marks, one of the marks would be for what is the inert pair effect, just the definition, and then the other 2/3 of the marks would be for why does it happen. So the definition I've just got at the top here. So it's the tendency of the oxidation state too lower than the maximum to be more stable at the bottom of the group. So let's take the example in the question to look at it. So we've got silicon, which is fairly near the top of the group. It's in the 3rd period, carbon's above it in group 14. And then lead is near the bottom of the group, or at the bottom of the group. So with silicon, we know that's perfectly fine to be in an oxidation state of +4. For example, the oxide, let's look at those. As an oxide, we've seen that silicon forms silica, which is SiO2, silicon dioxide. If we go to the bottom of the group though, we see the inert pair effect in action. The oxidation state 2 lower than the maximum is more stable. So that means 2 lower than the maximum, oxidation state of +2 rather than +4. And if we look at the oxide of lead, it does just make PbO. If we try to make PbO2, and yeah, have an oxidation state of +4 is very unstable, and it's a powerful oxidizing agent. So that's the definition. The tendency of the oxidation state 2 lower than the maximum to be more stable at the bottom of the group. And now it comes to the why. And I've got sort of a 5-step plan to write out for you to describe it. So before I've used the valence bond theory to illustrate this as well, which can be very helpful. The reason I'm not going to do it now is that even though every time I give the example it is for like lead and silicon or lead and carbon in group 14, the inert pair effect also happens in group 15 with things like nitrogen, and that's a lot harder to show picture form using this valence bond energy diagram I have. So I want to give an example without the energy diagram as well. So the first one is that for the maximum oxidation state to be reached, the NS2 electrons, which we'll call E-, have to be involved. If they're not involved, this is actually what the inert pair is from the inert pair effect. Now, if we want to get these NS2 electrons in bonding, I mean, they're already a pair in an orbital. They're perfectly happy to exist how they do. If we want to get them involved in the bonding, there's an energy cost to it. So they've got to, in the example when I was using the valence bond theory, I showed how they can, they first get promoted to a p orbital and then they hybridize to this sp3. There's the energy cost of it going from the s orbital to the sp3 orbital, which is a very good explanation, illustration. But as I say, this time, if you want to be able to explain it in terms of, say, phosphorus as well, let's do it without that energy diagram. So it takes energy to get these NS2, this pair of s electrons involved, and let's call that an energy debt. Like if we're promoting it and putting energy in, we need to recover this debt or it's not going to happen. And how the energy debt is usually paid off is the making of bonds. So in the example of the silicon dioxide, if we want these the NS2 electrons to be involved in bonding, there's the energy cost. But by making these two silicon oxygen bonds, the energy gained from making the bonds pays off the debt. Pays off the debt. And the energy recuperated or paying off the debt is related to the bond enthalpy. So if we're making strong bonds, we're getting a lot of energy back and we're offsetting this debt. However, as we go down the group, we know that bond enthalpy decreases. There's two words. Enthalpy decreases. This is because of things we've said before, such as the atomic radius getting much bigger as we go down the groups. There's less overlap of orbitals and it becomes a weaker bond, so it's got lower bond enthalpy. And that's the case in the lead oxygen bond. If you were trying to make it with 2 oxygen bonds, you'd have to get these NS2 electrons involved. That would cost energy. You'd have this energy debt. But the bond enthalpy of lead oxygen is essentially too poor to pay off this energy debt. It's a very weak bond, so too poor to pay. So that's how the bond enthalpy comes into it. You need a high bond enthalpy at the top of the group to recuperate this energy cost of getting the NS2 electrons involved. And then for my 5th point, I have it a star rather than a point. It's like a bonus point. There's also at the bottom of the group the effect of the D block. So at the top, carbon and silicon, there aren't the the transition metals in the way. Whereas when we get to the bottom of the group with lead, you've got the transition metal. And we've talked before in one of the lectures how these d orbitals aren't very good at shielding. So at the bottom of the group with lead, the nucleus has lots and lots more protons added, but the d orbitals and the electrons in the d orbitals aren't very shielding, which means that the s electrons are actually, quite strongly held. They've got a high Z effective charge, d block influence. So the d block influence, these ns2 electrons are quite strongly held. They've got high Z effective charge, and therefore it's like a double whammy. Not only is the bond enthalpy lower at the bottom of the group, but the energy cost is higher. So there's a much bigger debt and not enough bond energy to pay it with. So that's what the inert pair effect is and why it happens. The final question in lecture 6 is question 10, which is asking us to calculate the enthalpy changes of formation for PCl3 and Pi3, and then using these to comment on the stability of each of them. So the textbook actually gives an example or like a general enthalpy cycle for the formation of group 15 halides on page 1245, sorry. And then from the bottom of page 1245 to page 1246, there's a very similar example to this question, except what they're using is nitrogen rather than phosphorus. So if you want to see it in the book and do like a worked example that way, it's on page 1245 and 1246. But I'll take their general enthalpy diagram and we'll work from there to go through this question together. So they give the general formula as A plus N over 2 halogens goes to AXN. And this is the enthalpy change of formation for whatever we want, AXN. Now, what A is really depends on which element, and the stoichiometry might change. But when it comes to actually getting A as an atom in the gas phase, which is what it's reacting at, it's the formation enthalpy of this element. And because it's the enthalpy change of this element and it's relating to what's formed down here, it doesn't actually matter what the stoichiometry and how it starts up here is. You can just use, if you just want one of A, which in our case will be phosphorus, you just use one of the enthalpy of formation of it. We then need to get the halogen in the gas phase to react with it as well. So then we end up with N halogens, and this takes N times the formation enthalpies of this halogen. This is exactly the same. If you want to, we'll want to make three chlorines or 3 iodine atoms. So N is 3, and then we have to do 3 times the enthalpy change of formation for an iodine or a chlorine. And then the final step and thermodynamic term we need is this one, the reaction between the group 15 element and the halide to make the compound. And this is minus N, the bond enthalpy that's being formed. So it seems complicated at first, but let's relate it to something we've done a lot of already, and that's the ionic solids and enthalpy diagrams for them. So this last step, we'd usually use minus the lattice enthalpy, or the lattice energy if we were calculating it using the Kapuscinski equation. And that's because, the definition of the lattice enthalpy was the amount of energy that was given out when we broke the solid down into its gaseous ions. This is almost exactly the same, but for covalent compounds. So rather than being an infinite lattice with so much energy in it, covalent compounds are much more discrete. It's just PCl3, and the energy is just contained in the covalent bond between the phosphorus and the chlorine. And for much in the same way that we'd use the minus lattice energy, we're using minus the bond enthalpy. So the bond enthalpy is the energy released when the AX covalent bond is broken into A and X. We're taking A and X individually and making the bond, so it's the minus. And again, the N is here because we're going to be making 3 or however many AX bonds. We times it so it's stoichiometrically correct. So let's look at what all these A, X and N's are for our cycle. So A is going to be phosphorus, B. X is either chlorine or iodine, because we want to know them both. And then N is going to be 3. And that's because, yeah, we can see from the formula is PCl3 and PI3. Now, if you really want to know what this is going to be, to make it more correct, sorry, in this one, the term A at the top here, I'd imagine it would be a quarter of P4. Because this is if we're using a white phosphorus, so you know, the very reactive one we saw in the lectures. They made the P4 tetrahedra. But as I said previously, what is up here won't make a difference to our calculation because we're looking at the bond enthalpy of a mole of phosphorus. So then, yeah, let's solve it essentially. So we're looking for the enthalpy of formation for AX3, we'll say, because we know it's going to be phosphorus trichloride or triiodide, and that equals the enthalpy of formation of, so I'll stop referring it to A and start calling it phosphorus because it's a constant one here, plus 3 times the enthalpy change of formation of X, so the halide, either chlorine or iodine, minus 3 times the bond enthalpy of Px. So either 3 times the phosphorus chlorine bond enthalpy or 3 times the phosphorus iodine enthalpy. And remember, we're minusing this value because we're creating the bonds and not breaking them. So then if we add all the numbers in, and we'll do it for PCl3 and PI3 at the same time. So the enthalpy change of formation for a mole of phosphorus is 315. That's the same for both of them. Then we need to do 3 times the formation energy of a mole of halogen. So for chlorine, that is 121 kilojoules per mole, and for iodine, we're going to get 3 times 107 kilojoules per mole. And then finally, we're taking away 3 times the bond enthalpies, and for the phosphorus chlorine, it's 326, and for iodine, that's 3 times 184. And then if we do all of these sums, we find that for PCl3, the enthalpy of formation is minus 300 kilojoules per mole, and for PI3, it's 84. So what can we tell from this? That was the question, is comment on the stability of these compounds. So phosphorus trichloride, the PCl3, is exothermic energy of formation. Therefore, we know it's thermodynamically favourable to make it, and therefore this is a stable compound. But PI3 has a positive enthalpy of formation. It's it would be endothermic, so it's not stable with respect to the elements. So it would rather be phosphorus and iodine rather than PI3. And we can see that this is mainly because of the big difference in bond enthalpy. So we've talked already with the inert pair effect, how you go when you go down a group, bond enthalpy decreases because of the size of the atoms and whatnot. And we see that again here. So iodine's much lower down the group. It's got a lower bond enthalpy than chlorine, and this makes it less stable.